Now let us discuss about the preparation of aldehyde and ketones. Now this is a very important topic for any exam, whether it's a CBSE or NEET or JEE mains. And aldehyde and ketones, they both contains a carbonyl group. And this is carbonyl group in which the carbon is sp2 hybridized and has a trigonal planar shape with a bond angle of 120 degree. And we have number of methods to prepare aldehyde and ketones, and all these methods are equally important. Now the first method is from alcohol, from hydroxy functional group alcohol. Now this is primary alcohol. Any compound containing CH2OH group is called primary alcohol. Now this primary alcohol can be changed into aldehyde. It doesn't matter which R group is present. Just look at the functional group CH2OH. Can be changed into aldehyde either using a mild oxidizing agent PCC. This is oxidation. We are supplying oxygen. And the side product is H2O. So I am writing minus H2O. This is called oxidation, mild oxidation. And PCC oxidizes only alcohol. It does not affect the other functional groups. Or we can use copper at 300 degrees Celsius. Now here we are not supplying any oxygen, but we are able to remove two hydrogens. So this reaction is called dehydrogenation. This is not called oxidation. We are not supplying any oxygen. We are not using any oxidizing agent. Copper is used only to provide a surface, and it is the effect of heat which results in the loss of two hydrogen atoms and gives an aldehyde. And similarly, a 2-degree alcohol, any compound containing CHOH group is called 2-degree alcohol, and these two alkyl groups, they may be same, they may be different, it doesn't matter. It's alkyl, it may be cyclic, it can be any alkyl group. Now again in this case, mild oxidation with PCC, pyridinium chlorochromate, results in the formation of a ketone. So 2-degree alcohol gives ketone. There is no change in the number of carbon atoms. There is no change in the arrangement of carbon atoms. Or we can use a copper at 300 degrees Celsius, which is called dehydrogenation. Now suppose we have a question that prepare propanone by dehydrogenation method. Now this is very specific. You cannot use any other reaction except dehydrogenation, loss of hydrogen. So this is propanone, and we write a corresponding 2-degree alcohol on the left hand side. This is 2-degree alcohol, propane 2-ol, and we write the reagent, we write the conditions, copper at 300 degrees Celsius. So in this case, you cannot use PCC, that is the mild oxidation. Here it is mentioned dehydrogenation. Now the second method is from alkenes using reductive ozonolysis. Reductive ozonolysis. Now in this case, the final product depends on the structure of the parent alkene. And you just remember one line, that ozone attacks only at the double bonded carbons. So we write ozone followed by a reaction with zinc and water or zinc and acetic acid. And this ozone oxidizes only the double bonded carbon. And if hydrogen is present, if H present at the double bonded carbon, then it gets oxidized, or then it gives an aldehyde otherwise ketone. So this one line you have to remember. It doesn't matter what type of alkene is given to you. So look at the double bonded carbon. If hydrogen present, then aldehyde, otherwise ketone. So in this case, the two products are, one is aldehyde, carbon A gets oxidized to aldehyde, while the carbon B gets oxidized to ketone. So it may give you a mixture of aldehyde, mixture of ketones, aldehyde plus ketone, to same aldehyde, to same ketone, to different aldehyde, to different ketones. It doesn't matter. Look at the parent alkene. Now this is one example. Now this is the alkene given, and we are performing an ozonolysis using ozone followed by reaction with zinc and acetic acid. Now in this case, the two products are obtained. Carbon A gets oxidized to aldehyde, carbon B gets oxidized to ketone. So the aldehyde obtained is this, and the ketone is acetone in this case. So this is B, this is A. Now the third method is hydration of alkynes. Hydration of alkynes using dilute sulfuric acid. Dilute means water in the presence of a sulfuric acid and mercuric sulfate, mercuric ion. And remember, this condition is used only with alkynes, not with any other functional group. Now in this case, we have to add water. So if this is alkyne given and we are adding water to this in the presence of a sulfuric acid and mercuric sulfate, so H adds to one carbon and OH adds to the second carbon of the triple bond, and it gets converted into, this is called enol form. En means double bond and ol means alcohol, and both are at the same carbon. That's why this is called enol. And enols are generally unstable. They undergo tautomerism to form a carbonyl group. So this double bond shift to this side, H shift to this side. This may be aldehyde, may be ketone. So if alkyne is symmetrical, you add OH minus of water to any carbon of the triple bond, and if it is unsymmetrical, you have to follow Markovnikov's rule. Now these are the two examples. Now this is symmetrical alkene, this is symmetrical alkyne, so you can add OH minus to any carbon of the triple bond. So we are writing dilute sulfuric acid, mercuric sulfate, and this is the enol form obtained. And this enol form then undergo tautomerism to give acetaldehyde as a final product. Now this is unsymmetrical alkyne, propyne, so you have to follow Markovnikov's rule. So addition of water in this case takes place according to Markovnikov's rule, and the enol is this. This is the enol obtained, but enol is again unstable, tautomerized to give this ketone as the final product, acetone. Now the next method is from acid chloride. This is called acid chloride, chloride of a carboxylic acid. Look at this group only, and we can prepare both aldehyde and ketones from the acid chloride. Now this is acid chloride. If we want to prepare aldehyde, then we replace the chlorine by H. This is addition of hydrogen. This is removal of electronegative atom. So this is called reduction. And we use a reagent H2 palladium and barium sulfate. This is called Rosenmund's reduction, very, very important reaction in organic chemistry, Rosenmund's reduction. So in this case, the number of carbons remain same, arrangement of carbons remain same, you just replace the chlorine by hydrogen. For example, this is given, this is a benzoyl chloride and we are using H2 palladium BaSO4. So the chlorine has to be replaced by hydrogen and it gives a benzaldehyde. Now we can also prepare ketones starting with acid chloride. So in this case, now we have to replace this chlorine by some alkyl group. Maybe same, maybe a different. Now this is an example of a nucleophilic substitution. So we are looking for some reagent where the alkyl group is present as a negative part. So here we use dialkyl cadmium. And we cannot use the Grignard's reagent here because the magnesium is more reactive than cadmium. So that Grignard reagent with acid chloride results in the formation of a 3-degree alcohol. So we are using a less reactive metal, cadmium. So the side product is CdCl2. This is a very good method to prepare any type of ketone. This is an example of a SN2 reaction. So the acid chloride has to be less crowded. So this is one example. So this is dibenzyl cadmium. Dibenzyl cadmium. So on reaction with the CH3COCl, it gives benzyl methyl ketone. So this is the ketone obtained. Now fifth method is from the cyanides. And again we can prepare both aldehyde and ketones starting with cyanide. Now this is cyanide, this is the cyanide carbon. And by reacting it with SnCl2, HCl and followed by hydrolysis, this cyanide carbon can be changed into an aldehyde. This is called a Stephen's reaction. Stephen's reaction. And the CN group can also be changed into an aldehyde by using a Debal H. And this cyanide carbon can be changed into ketone using a Grignard reagent followed by hydrolysis. The CN carbon can be changed into a ketone. And again these two alkyl groups, they may be same, they may be different. Now next is how to prepare aromatic aldehyde and ketones. Aromatic aldehydes and ketones. And the important aromatic aldehyde is benzaldehyde. And the benzaldehyde can be obtained or can be prepared starting with the toluene. Now this is toluene, methyl benzene, and this carbon can be changed into aldehyde via 3 different methods. One is by using a chromyl chloride, CrO2Cl2, carbon disulfide used as a solvent followed by hydrolysis. This can be changed into aldehyde. It's a mild oxidation, and this reaction is called Itard's reaction. The second method is reacting it with a chlorine in the presence of a light and heat. This saturated carbon H can be replaced by chlorine. Now these two chlorine atoms are on the side chain, not directly bonded to benzene. So these two chlorine behaves as an alkyl halide. Alkyl chloride can be hydrolyzed very easily by the moisture in the air to form a benzaldehyde. And the third method is reacting it with a chromic acid, CrO3, in the presence of an acetic anhydride, and it gives an ester. This is the intermediate obtained. And this on hydrolysis gives a benzaldehyde. And the formation of this ester as an intermediate is to prevent the oxidation of methyl benzene directly to benzoic acid. So if there is no acetic anhydride, no ester form as an intermediate, then CrO3 will oxidize the toluene directly to benzoic acid. And the aromatic ketone can be obtained by using the Friedel-Crafts acylation. Friedel-Crafts acylation. So reacting the benzene with acid chloride which contains benzene or alkyl group in the presence of AlCl3 as a catalyst, it gives an aromatic ketone. Now one example is this: we are reacting the benzene with benzoyl chloride, C6H5COCl. This is called a benzoyl chloride. So you have to be very careful. It's a benzoyl chloride, not benzyl. In the presence of anhydrous AlCl3, it gives a benzophenone or diphenyl ketone. This is called diphenyl ketone or a benzophenone. This is very important conversion also. Sometimes they give a question, write the structure of the benzophenone. So this is about the preparation of aldehyde and ketones.